Welcome back. We are now up to chapter 23. I hope the weekend has been a good one for you. And we're going to be talking about the death of stars and other fascinating things this week. I think in some ways, this week's material, both for this chapter and chapter 24, are some of the most interesting chapters that we have. And it certainly was one of the areas of inspiration for me when I was about 10 years old and learning about things like white dwarfs and neutron stars and pulsars and black holes that really caused me to get interested in astronomy as a large-scale thing. I was interested in planets and moons and other places we could visit, but in terms of cosmology and understanding what's out there in the universe and how and why and where and all the different possibilities, this was just really, oh my goodness. So I invite you to join me as we're looking at some of the more bizarre things in the universe. And let's see, I want to share the screen. I want to, let's see, it keeps telling me other things. So I don't know if you're seeing this when I'm doing this, but there we are. Okay. So we're up to the death of stars, and by which we mean, of course, the things out in the universe and not people in Hollywood. When we're looking at different things out in the universe, we're seeing a recycling pattern. We've talked about that before. When we look at a nebula such as this, we're seeing new and old crunched together. One of the things that, of course, is happening here is a lot of the gas that's around has come from previous stellar events, stars that have exploded and returned their material back out into space. Some of the other blobs are things that are forming into new stars. We've talked about the life cycle of stars. But one of the things that we haven't talked about very much is what happens at the end. So that's what we're going to be doing here. When a star is on the main sequence, if you sort of remember the main sequence, it looks a lot like this, but this is not a view of the main sequence. This is a view of what happens after the main sequence. And it's interesting that it takes a similar form when we're looking at it like this, because we would have our low mass stars here, we would have our high mass stars here. When we're looking at this particular chart, we're looking at the leftover of lower mass stars, stars that are the size of the sun or less, not too much larger than the sun. And we're looking at the lower mass stars up here and the higher mass down here along the way. But what's left over when we have a star like our sun shed its material off into a planetary nebula is called a white dwarf, and that's sort of the exposed core that's left over. One of the persons who's perhaps most notable in the 20th century for figuring out the sort of astrophysics of all of this is a guy named Chandrasekhar. He spent almost all of his life, his academic life, his professional life at the University of Chicago, so not too far from us. Notice the dates of his life there. By 1933, which means he was only 23 years old at that time, he had already figured out enough to get himself a PhD and a fellowship and all sorts of things from Cambridge University. And he'd also already figured out enough to win the Nobel Prize, which was not awarded for another 50 years. He actually was going to have this brilliant career in the British schooling system. But there was another guy who was sort of the grand old man of astronomy at that time named Arthur Eddington. And Eddington had many good qualities, but one of the ones that was not so good is he tended to be prejudiced towards people who didn't look like him. And Chandrasekhar made no secret of this later in his career, that one of the reasons why he did not stay, wasn't able to stay in Britain and work with the astrophysical community there, was because of Eddington's racial prejudices. So what was their loss became America's benefit. And he was courted by lots and lots of places. He was offered a Harvard fellowship. He was offered directorship of things at Princeton. He turned them down. He ended up staying at the University of Chicago. He is such an important educator. Two of his students actually won the Nobel Prize before he himself won the Nobel Prize. I mean, think about that. Think about that. One of the great observatories, one of the great NASA observatories in space, Hubble is one of those, is called the Chandra after him. And it's the one that looks for X-rays. And that's one of the things that we figure out when we're looking for white dwarfs, more particularly pulsars and especially black holes. We're looking for X-rays. So we'll be talking about that. So remember that name, Chandrasekhar. You had to call him Chandrasekhar until you got your PhD, and after that you could call him Chandra. We'll call him Chandra because that's what the probe, the observatory telescope is named. But white dwarfs, what is a white dwarf? A white dwarf is the remaining core of a dead star, but it can't be above a certain limit. Guess what? That limit is called the Chandrasekhar limit. He was the guy who figured out how large things could be before they imploded and more and more and more and crushed down in. So we call that the Chandrasekhar limit to this day. Our guy Eddington, who is not so hot all of the time, publicly ridiculed this in like 1935. By the time the 70s rolled around and we had computers and were verifying black holes and other kinds of things, everyone was like, no, he was right after all. Of course, Eddington had been dead since 1944, but can't win them all. Chandra lived to see his reputation more than praised and sort of redeemed in that degree. But what happens inside of white dwarfs? They actually shrink down very, very small. If we have stars that are about the size of our sun or maybe less, we have this sequence that we talked about before where they begin to balloon out, they begin to burn some helium if they can, they shed their outer core or their outer layers to expose the core. What happens to that core? Well, we sort of move that all the way down here to this portion of the HR diagram where they're very, very hot and luminous, but they're slowly cooling off because they're not actually generating any more energy. They're just like if you turn the engine off of the car, but it takes a while to cool off. That's what's happening here for the white dwarf. But if you take a star the size of our sun, which if this were the size of the Earth on your screen here, the size of the sun would take up more than your house that you're in there today. The leftover core gets scrunched down into something maybe about the size of the Earth. So think about something, say the size of your car being scrunched down into the size of a soda can. And yet you've got almost the whole mass of your car in that soda can. You can't pick it up, it's too dense. That's what's happening here. The density of matter on this is going to be so much that if you had that sand bucket full of material from a white dwarf at one size of our sun, it's going to weigh more than Mount Everest, maybe as much as most of the Himalayas along the way. But here's the ironic thing. The more material you get that's left over, the more it packs it down, and the more it packs it down, and the more it packs it down. So it's like if you had a car, say a Honda Civic or something like that, that would crunch down into the size of a soda can. But if you had a much bigger car like a Cadillac, that would scrunch down into the size of a D-cell battery. So if we had a star that was just 30% larger than our sun, notice that the actual volume, the size, goes down. But there, that bucket of stuff is going to weigh even more because you're scrunching more and more and more stuff into the white dwarf. What we have happening is that the electrons, which if this was the nucleus, the electrons are way out here. How far is way out here? You may remember when we were talking a little bit about the inside of an atom. If this was our nucleus, the electron would be circling way out by the moon. Well, the thing is, as we are getting this much material, scrunch, scrunch, crunch, they're pushing the electrons in closer and closer and closer and closer. So that's why the more you have, the smaller it gets, all the way up to about 1.4, maybe 1.44. So about 40 to 45% larger than the sun. What's happening is it's scrunching further and further and further down. This is the limit. If you get more mass than this is the Chandrasekhar limit, then it's going to scrunch down into something else. The electrons that are pushing out can't push out anymore. So what happens there? We have, of course, our white dwarfs. We talked about this evolutionary track. This is what will happen with our sun. We can see white dwarfs around. Hold that thought about what happens when we exceed the limit. We're getting there. We can see white dwarfs that are out there. One of the better known ones is the companion star to Sirius. Sirius, of course, big bright star, brightest star in our sky at night. It's not brighter than Jupiter. Jupiter is not a star. Not brighter than Saturn. Saturn's not a star. Not brighter than Venus. Venus is not a star. It's the brightest star in the sky at night. We're saying night because the sun is the brighter star during the day. But it's actually two stars. And when we are looking at it through a telescope, we can sometimes resolve it into two. This is an X-ray one made with our Chandra Space Telescope, yay Chandra, there. And one of the things that we can note is that things are reversed. In X-rays, the white dwarf is brighter. In actual visual light over here, the white dwarf is almost invisible. It changes depending upon what kinds of things you're looking at, which means lots of X-ray stuff is happening here. What could possibly happen that would make this happen? You might look at the thing that I have up behind me. We're going to get to that here too. That is a binary system where you have two stars. Most binary systems do not have twin stars. One of the things that can happen is you can have material leached off from one star to another. So one of the better known examples of that right now is a star called Algol. I think I talked about star naming earlier in the semester, where if you have an AL, that comes from an Islamic catalog. They used to be during the golden age of Muslim astronomy, great catalogers and great observational astronomers, and we keep a lot of the names from that. Well, Algol had two stars, one that was higher mass, one that was lower mass. The higher mass one, of course, dies sooner, which means it balloons out more sooner. But as that happens, it might get a little too close to its companion, depending upon how close they are at the start. Well, in Algol, they were relatively close. And so as the bigger, brighter star began to balloon out in its old age, the gravity from the other star started pulling material in to it. This is called mass exchange. Sometimes what will happen, though, is that this material will fall in as a disk of material if the other binary star, the other star in the binary, is a white dwarf. If it's actually already gone through this phase and has now collapsed down into its leftover core, it will begin pulling stuff off and it will create an accretion disk. These accretion disks glow from friction that's happening as the stuff is spinning and as more stuff is being pulled in, and that glow causes the X-rays, among other types of energy, but in particular X-rays. And what will sometimes happen is that this white dwarf accretion disk will reach a certain mass and then explode, and we call this a nova, which basically means new star. But what's happening, of course, is it's not a new star, and because this is an ongoing process, it will happen again and again and again and again. So we have a lot of novae, that's the plural for nova, that will happen on a regular basis. I won't say frequent because there can be a lot of time between these sometimes, but it will happen on a regular basis. So what we have is one star temporarily getting much brighter because of the explosion, and it drives material, it drives matter out. That explosion begins to drive material out again. So when we've got a really, really massive old star, as we talked about before, we have all of these different shells inside that are burning at the same time because it takes less to burn the hydrogen than it does the helium. It takes less to burn the helium than the carbon, and so on, all the way down to iron. Remember, we talked about iron being the sort of the end of the road, because for iron to fuse, you actually have to put more energy into it than it will give out. So you have this complex but pretty unstable grouping inside, sort of like an onion. So when that happens, we end up with a supernova explosion. Supernova is when the star itself explodes. Nova is when that accretion disk explodes. So they are very, very different kinds of things. But one of the things they share in common is they both become very, very, very bright. Sort of notice here we have our brightness, we have our brightness here, we have our brightness here. The top row here, we can sort of see that this clearly outshines the entire galaxy it's in. This one comes close to outshining it. This one gives us a lot of material as well. So these are a massive, massive amount of material and a massive, massive amount of energy that happens. A massive star supernova is when all of those layers destabilize and the iron core reaches what we would call the Chandrasekhar limit, the white dwarf limit, and it collapses even further than a white dwarf. It collapses into a neutron star. A white dwarf supernova, on the other hand, is one of the things that happens when it reaches that limit with an explosion where the carbon, so we're going beyond carbon in the massive star supernova, we're only getting up to carbon in the white dwarf supernova. So we have two different types of supernovae, and these are both, again, different from the nova, which is the disk of material exploding along the way. We can tell from the light curves which one's which, because the white dwarf supernova will actually initially seem to be a little bit brighter and will have a steadier decrease, whereas the massive star supernova will be a little bit more bumpy along the way over the course of time. Notice these times here. They don't last for a very long time when we're talking about things in a universal sense. We're talking about less than a year to a little bit over a year that you're sort of seeing what's happening there. That's why if one happens in our neighborhood, you may remember my talking about my guy Tycho with the fake nose. He saw a supernova. We call it to this day Tycho's supernova. And he saw this and he cataloged it for more than a year. He was able to sort of chart what it looked like until it completely disappeared, until we got telescopes and we could find it again, because there's this huge sort of nebula all around it along the way. Not only did Tycho have one in the late 1500s, but Kepler, his assistant, saw one in the next century, in the early 1600s. We typically only get one per century on average. We haven't had one since Kepler almost 400 years ago. That's why Betelgeuse. We're hoping we're going to have one not too long from now. It would be wonderful to have one with all our modern technology along the way. But what's happening, of course, is we can no longer see the Kepler supernova. We can no longer see the Tycho supernova. We can see the remnants because we know where they happened. They were cataloged by these expert astronomers in such a good way that we know exactly where they were. When we're looking at the different types of imagery here, we have two different X-ray visions. We have an infrared vision from the Spitzer. I've talked about the Spitzer before. When we look at the Hubble, notice we're not seeing a lot in the Roy G. Biv area along the way. So when we're looking at this kind of image, what we're really looking at is a composite image. We have taken the X-rays, the infrared, bumped the X-rays down, bumped the infrared up, put them together with the visible. So this is what we could see if we could expand our vision to see into the X-ray and into the infrared visions along the way. This is another supernova remnant. You can see it's not that old because it's very uniform in the same way the Kepler one is. It takes a while for them to become mishmashy. If they're still sort of in the process of billowing out from the explosion, that can actually take thousands of years along the way. So here's one that was discovered not too long ago. We have this one in one of our nearby galaxies. Again, we have our Messier catalog here. This one is a white dwarf in another star that's happening, but this little thing that you can see here was detected as people were sort of looking at images and saying, hey, that wasn't there once before. This is essentially how we do it when we're looking for these kinds of events. We're comparing pictures we take now with pictures we've taken before and hoping that we detect things like this. This one isn't a particularly bright supernova because one of the things that we notice is the whole galaxy, the whole cigar galaxy here is very bright by itself, but it's still bright enough to be seen through the gas and dust that's there. And if it wasn't there before and is there now, we know it's not just a sort of standard star unless the gas and dust is dissipating. And that's when you have to sort of begin your analysis to see what kind of light curve you're getting off of it along the way. Here's another one. Notice in the middle here, we've got this little ring kind of system here. We've got different images from what's called the 1987 supernova. SN stands for supernova. And this is from a nearby galaxy, our Large Magellanic Cloud, one of our two closest galaxies. And you can see that in the southern hemisphere. So these, of course, were from images that we've been taking over and over and over again. And it can be quite fascinating to look at them over the course of time. This is a close-up of the supernova explosion that's in the center. If you look right here in the center, what's happening there, we can see what's happening over the course of just these few years, that you're getting a more fragmentary kind of system that's happening and a more dissipated system that we have along the way here. So when we're talking about when it actually happened 30,000 years ago, well, it took that long for the light to get to us. So even though it happened 30,000 years ago, we're sort of watching it unfold in almost real time as we're looking at these kinds of things. And again, we have that sort of bumpiness that's happening. And we can see its curve is going a little bit longer along the way than we have in some of the other models, but the overall pattern stays the same. Then we see things like this, which we sometimes won't see a star in the center. And we might see a star in the center in X-rays, but we won't see a star in the center in Roy G. Biv kind of light. This would be a neutron star. What's happening here is literally the electrons are being squeezed in to the nucleus. They're literally, instead of going around and around and around and around and around in smaller and smaller circles, they're actually being squeezed all the way in to the nuclei, which means the electrons, which are a minus, and the protons, which are a plus, get wiped out. Neutrons are neutral. They cancel each other out. And so this is part of why it's called a neutron star. What happens is, of course, is that these things crunch down and there's no more space in the atom sort of holding anything up along the way. So we no longer have what's called electron degeneracy. We now have neutron strength that's happening. And then remember, a star one size or one mass of the sun gets to be about Earth size, and 1.3 gets to be maybe about moon size, and 1.4 maybe gets to be a little bit under moon size. Well, by the time we get to say 2 or 3 and it turns into a neutron star, it drops down to about the size of Bloomington, or about the size of Lansing, Michigan. I think whoever made up our textbook in part went to Michigan or maybe it works there, so they chose Lansing. I would choose Bloomington along the way. But instead of being 5,000 miles across or 3,000 miles across, it's going to be about 5 miles across. And that same sand bucket of material, instead of weighing as much as Mount Everest or all of the Himalayas, is now going to weigh about as much as the Asian continent. It's like pretty heavy there. When we look at the Crab Nebula, which we've looked at before, at the center there is not a white dwarf. We look and we look and we look and we can't see it. But when we look at it in X-rays, we can see this happening there. There's something pulsing there. That's a neutron star that is spinning around really fast and creating energetic sort of echoes and energetic pulses that come to us. And the pulsar there is going 30 times per second. That's a lot of stuff to be whipping around 2 to 3 times this mass of the sun, shrunken down. Again, think about an ice skater who has her arms out. She's sort of going around in circles. I never know how they stay up there because I do the thing with the baseball bat, and after 2 or 3, it's like, I don't need to drink, I'm drunk. And she's just, but as she pulls her arms in, she goes faster. She puts her arms out, she goes slower, but she pulls her arms in, she goes faster. What's happened here is they pulled this massive star down to the size of Bloomington. So it's whipping around really, really, really fast. When we first detected pulsars like this, we had no idea what pulsars were. We had no idea that you could have neutron stars. We had no idea what the degeneracy things were with electrons and neutrons and such. And so we thought this might be cosmic GPS. This might be the signal that spaceships use to keep track of each other. And there was serious debate for a while, a short while, but still a while, of saying, we found extraterrestrial intelligence. That's not the first time nor the last time that's sort of been the determination before we've like, whoa, we have some natural explanations here. But yeah, in the center of our Crab Nebula, that star that everyone could see and read by at night and see during the daytime, except the Europeans, in 1054, at the dead center of this is a pulsar. And notice that what's happening here, this isn't the same sort of gentle sort of bubbling out. This is a little more energetic of a splatter that's happening there. But when we look at pulsars, they act in many ways like a lighthouse would, which is why people thought, well, these could be lighthouses in space for intelligent spacefarers. And in fact, if we ever do get out into spacefaring, we will use them as our guideposts because they're great natural lighthouses along the way. But the lighthouse rotates and sends its light out in a particular form, in a particular pattern. So it doesn't just sort of do it willy-nilly and everything. As pulsars are spinning, they have these jets of energy where most of their energy is also going. Just like with the lighthouse, you don't have to be right in the line of sight to see it. You also don't have to be right in the line of sight to see a pulsar, but you get a lot more energy if you are in the line of sight, which is going to be from the rotational magnetic axis. So as it rotates, it also has a magnetic field, and that magnetic field, just like our magnetic field interacting with the solar wind gives us the aurora borealis, magnetic fields with this kind of energy, with this kind of spin, is going to just shoot off energy. It's going to beam radiation out there along the way. So what we're having, of course, is we have our magnetic poles and we have our rotational axis poles. Those don't always match up. In fact, they most of the time don't seem to line up. But we're not usually in the direct line of the beams of particles and radiation that are happening. So we get to see a little bit at an angle of different pulsars that are out there. One of the things that we see in this picture along the way. We sort of see this interesting little thing down here in the bottom. One of the things that we are seeing here, this is 37 light years across. The nearest star to us is 4 light years away. Sirius, the brightest star, is 8 light years away. So this is a long kind of jet trail that's happening. As the picture here says, this is the longest ever observed in the Milky Way in terms of what's happening here. So we have a pulsar that is moving away from the core of the supernova remnant where it originated at a phenomenal speed, and it's really quite something that we have here. But here we can see sort of, again, not to scale, very much so, what might happen if we had different kinds of stellar evolutions in tandem with each other. Because most stars out there are actually part of binary or trinary or cluster kinds of situations. We'll have one star that's bigger than the other, which means it will evolve faster. It may turn into a white dwarf, which then the other main sequence star may have some cannibalization happening, and we'll get the type 1A supernova where the white dwarf explodes along the way when we reach those magical Chandrasekhar limits. We can have matter falling into a white dwarf. We can also have matter falling into a neutron star. So this kind of accretion disk situation can happen in either case. It can also happen, remember this for chapter 24, in a black hole situation. That accreting matter doesn't just fall in, it spirals in. And that spiraling in, it increases its speed as it's going in. It has angular momentum that it adds to it. It increases the neutron star mass and spin, and it generates all sorts of X-rays along the way. So a lot of this happens. And we will have our X-ray bursts. And that's one of the things that we see with the Chandra Observatory. We have a lot of data from that. They also can generate gamma ray bursts. And we have the Compton Gamma Ray Observatory for use for that. It's one of the NASA great observatories as well along the way. So we have bursts of gamma rays all over the place in our galaxy. One of the things about gamma rays is they're even more energetic. They're even higher on the energy scale than X-rays are. So we will see these sometimes in our galaxy, but also a lot outside of our galaxy as well. And one of the things that we can do then is we can see in tandem with other observatories, try and get multiple images of what's happening here. Here we have the sort of different views that we have. Here we have the X-rays. Here we have our Roy G. Biv visible light with a little bit of ultraviolet modification along the way. So this is a kind of artist rendering of what might happen when we have a collapsing star that beats the Chandrasekhar limit for a white dwarf and beats the Chandrasekhar limit for neutron star, and is just so heavy that nothing's going to keep it together, so it collapses all together into a black hole. And when we're looking at that, one of the things we can also use, in addition to some of the NASA stuff, is stuff that is produced by our partners in space, like the Italians, the UK, the ESA, European Space Agency. The SWIFT space platform here looks for gamma rays and X-rays and ultraviolet. So one of the things that it does is it looks for sort of shorter bursts, and we're trying to figure out exactly what all of these kinds of things are along the way. And that's one of the mysteries we still have in astronomy, and we'll talk a little bit more about that in our next lecture. But for our next lecture, we will also be talking about black holes. So stay tuned for that.